In the previous video, I defined liquid pressure. I'm going to continue on with that concept, and we're going to start here by listing some important observations about liquid pressure. So imagine I have a container of a liquid. These little devices are meant for measuring pressure. Think of them as little springs, and when the pressure increases, it'll compress the spring more, and they're calibrated to read off of pressure. So the first observation I'm going to mention is that there is pressure everywhere in a fluid, not just at the bottom or at the walls of the container. That is a common misconception I've run into. Second observation is that the pressure at a given depth in the fluid is the same whether you point the pressure measuring device up, down, or sideways. So that's what they're showing here. So it doesn't matter which direction you point the measuring device, it always measures pressure, and if you're at the same depth, then you'll always measure the same pressure, no matter which direction you point. This is an important observation, and it's going to help explain other aspects of liquids. Last observation is that in a liquid, the pressure increases rapidly with depth below the surface. In a gas, however, the pressure is nearly the same at all points. That's assuming in a laboratory-sized container. So in a house, let's say you have two levels to your house. If you go up and down the stairs, you really won't notice a change in gas pressure. Liquid pressure, though, if you drop a foot, you'll definitely notice a change. So we'll talk more about gases in the next section on chapter 14. The observations I just listed can be used to explain the concept of buoyancy. In this figure, I'm showing an object that's completely submerged in a liquid. You can think of it as water or some other liquid. The arrows here are representing either force or pressure. It turns out that we can discuss either one. We know that liquid pressure increases with depth, so the bottom of this object has a greater pressure because it's at a greater depth. The top of the object has less depth, so there's less pressure pushing down on it. One of those observations said that there's pressure acting in all directions, so all sides of this object are going to feel an inward pressure or force relative to the object. But if you notice, if we think of these as force, there's more force pushing up on the object due to the greater depth, the greater liquid pressure, than there is forces pushing down. On the sides, the forces are actually equal and opposite because they're at the same depth. So if we add up all those force arrows, or you can think of them as pressure either way, what ends up happening is we find that there's a net upward push. That net upward push is what we call buoyancy, or the buoyant force. So we can define buoyancy then as an upward force on an object submerged in a fluid. This force is caused by the fact that the downward fluid pressure on the top of an object is less than the upward fluid pressure on the bottom of an object. When this object was placed in the water, it had to physically push liquid out of the way. So we call that liquid that was moved the displaced liquid, because it was displaced by the object when it was lowered into the water. Turns out that there's an important connection between the liquid that's been pushed out of the way, or what we call the displaced liquid, and the buoyant force on the object. It was actually a 3rd century BC Greek scientist named Archimedes who studied this. He came up with a useful principle that we still use today. The Archimedes principle states that an immersed object is buoyed up by a force equal to the weight of the fluid it displaced. When it says buoyed up by a force, that's most commonly referred to as just the buoyant force. And the key to this is that that buoyant force is equal to the weight of the fluid it displaced. So we really need to highlight it's the fluid it displaced. So another way we could state the Archimedes principle is the buoyant force is equal to the weight of the fluid that was pushed out of the way by the object when it was placed in the fluid. Maybe some demonstrations will help. So here, imagine I have a container that's so full of the liquid, or let's just say water, that anything else that's added to it will cause it to spill out. So now we have a rock that we're going to lower down into the water. You'll have to forgive my poor animation there, I just didn't have time to do any more. Anyway, we're going to lower it all the way down in so that water spilled out that whole time. Now, the total volume of this rock should equal the total volume that was pushed out of the way because it's completely submerged under the water. The Archimedes principle states that the immersed object is buoyed up by a force, so that's the buoyant force, that should be equal to the weight of the fluid it displaced. Or in other words, if we measure the weight of this water over here now, that should tell us the buoyant force that's pushing up on this rock. Here's an example with some actual numbers. So let's say we use a spring scale, that's what this thing is, to measure the weight of this mass and find that it's 7 pounds. Okay, so this object weighs 7 pounds when it's out of water. And then we're going to lower it into the water so it's fully submerged. And similar to the last one, this container is so full that as we lower it down, it's just going to spill out water. So by the time this is fully submerged, we should have an equal volume of water out here relative to the volume of the object. So let's kind of watch that. Okay, so here's a before and an after. This is before, this is after. All right, let's say we measure the weight of this water and we find that it's 3 pounds. What is the apparent weight of the object while it's underwater? What I mean by apparent weight is when this object is underwater, it should seem like it's lighter. And so the scale up here should not read 7 pounds because the object's going to seem like it's lighter. That's just what objects do when they're in water. So what would this scale read if we measured 3 pounds of water that was pushed out? Well, let's go through Archimedes' principle. So the buoyant force, or buoyed up by a force, is equal to the weight of the fluid it displaced. So the weight of the fluid it displaced is 3 pounds. So that means there should be 3 pounds of buoyant force pushing up. If there's 3 pounds supporting a 7-pound object, then we should be left with 4 pounds as what we call the apparent weight, meaning it appears to weigh less than it actually does. That's Archimedes' principle in action. All right, we're going to use the same principle, but I'm going to do something a little different this time. So I have an object that weighs 7 pounds again, but notice it's a different object. And this time, rather than submerging it completely under the water, I'm going to lower it down until it floats on top. So this object is at rest, floating on the surface. When I lowered it down, a certain amount of water was pushed out of the way. And even though this is a similar figure to the last one, don't assume it was 3 pounds. So I want to ask the question, if the object is floating on the surface, then what is the weight of the displaced water? Meaning if I were to weigh this right here, how much would it weigh? I'll give you a little time to think about that. Okay, to answer this question, we really should just look at the forces on the object. We know that the object weighs 7 pounds, which means there's weight or gravity pulling it down with 7 pounds of force. If the object is at rest floating on the surface, it must be in equilibrium, or in other words, no acceleration. That means the net force has to be 0 on it. If there's 7 pounds pulling it down, there must be 7 pounds pushing it up, so that the net force is now 0 and it's at rest. Well, that 7 pounds can only come from the buoyant force in this situation. So the weight of that water should be 7 pounds. So imagine this. This picture's representing a boat that's being slowly lowered into the water. So as the boat first starts pushing water out of the way, it's going to start feeling a buoyant force. The buoyant force is going to be equal to the weight of the water that was pushed out of the way. So they're trying to show that this amount of water was pushed out of the way. So if we could weigh that water, that would be the buoyant force. But if the buoyant force is smaller than the actual weight of the object, the boat's still going to continue to sink. As it sinks, it's going to push more water out of the way, so the buoyant force is going to increase, but it's still less than the weight, so the boat continues to lower itself into the water. Eventually, if you can hit a point where the weight of the boat is equal to the buoyant force, then it's just going to float on the surface, and that's really the ideal that you need for a boat. All right, read through this and see what you answer. Okay, so if we have a 4-pound object fully submerged underwater, it wants to know the buoyant force. I'm actually going to go with D, that we can't answer this unless we have more information. The reason why is because I never stated what the actual motion of the object was. Is the object just hovering at rest? Is it sinking? Is it rising? So neutrally buoyant is what I described as it's just hovering there at rest. It neither wants to sink nor float or rise. Without that information, we can't actually answer this question. Okay, now let's decide, well, what if the object was placed underwater like that and then released and it started to sink? If it starts to sink, that means the buoyant force must be less than its weight. So A would be my answer if I knew that it was sinking. If I knew it was rising, kind of like imagine you place a ping pong ball and you stick it under water, if you let it go, it's going to shoot up. So if that was the situation, then I would say the buoyant force is greater than 4 pounds. So I have more force pushing up than weight pulling down, which is why it rises. If it's neutrally buoyant, that means it doesn't care to rise or sink. The only way that can happen is if the buoyant force is exactly equal to the weight. So that would be the 4 pounds. So this is kind of a trick question. I would, on an exam, I would actually give you a little more information, but for now, I think it was a valid question. There's another way to decide if an object's going to sink or float, and that's by comparing the densities. This symbol here is representing density. It looks like a P, but it's actually a Greek letter rho. So that is a common symbol used for density. So rho F would be the density of the fluid. Rho O would be the density of the object. So I'm assuming this is the object that was put in the fluid, and then F is representing the fluid it's in. So if an object sinks, we know that the buoyant force has to be less than the weight. That's why there's a net force pointing down. That's why it's accelerating in the down direction, or in other words, sinking. I can't really prove this relationship to you because unfortunately we're not doing the math in this class. If I could go through some of the math in more detail, I could prove this to you fairly quickly. But for now, you'll just have to kind of trust me, I guess. It turns out that an object will always sink if the density of the fluid that it's in is less than the density of the object. An object will float, meaning the buoyant force is greater than the weight, if the density of the fluid is greater than the density of the object. An object will become neutrally buoyant, or doesn't try to sink or float, if the buoyant force is equal to the weight. That means that the density of the fluid must be equal to the density of the object. So if I write that out in words, An object that floats is less dense than the fluid. An object that sinks is more dense than the fluid. An object that neither floats nor sinks is the same average density as the fluid. Here I'm using the word average because really it's an issue of average. If the overall volume, if you take the mass and divide it by the overall volume, then that's where we're getting the density from. Okay, so let's look at this iceberg. One way to know for sure that ice is less dense than water is to just observe if it floats, and ice does. Now, you may have heard that for icebergs like this, a lot of the mass can be underwater, cannot be visible. That tells us that the density of ice must not be that much less than the density of water, because most of it is underwater. While we're on the topic of densities and sinking or floating, right now you see a metal coin that's on the surface of water. Is this coin floating? That's the question I want you to think about. Well, I guess it depends on what your definition of floating is. So from what we just talked about for densities, we said that if an object floats, it means it must have less density than the liquid it's in. However, the metal here definitely has more density than the water, so it should be sinking. The reason why it's not sinking is a different subject, but it's still worth our time to discuss. So here's the same principle with the paperclip. The paperclip, the metal in the paperclip is more dense than the water, so this paperclip should sink. If you don't believe me, just try it at home. Get a paperclip and put it in water. The key is notice the surface of the water, how it almost seems to be bending inward. You can see some surface features that sort of trace out the paperclip. What's happening is that water is made up of a bunch of individual water molecules, H2O. At the surface, the water molecules are actually bending inward to accommodate the weight of the paperclip. So it's not that it's floating in the traditional sense. That would mean that the buoyant force is equal to the weight of the paperclip. The paperclip should be sinking, but the water molecules have actually contracted. They've actually come together to support some of the weight of the paperclip. So they're creating a small upward force, just enough to keep it on the surface. This phenomenon is known as surface tension. I'll do my best to explain surface tension without making it too complicated. Here, imagine that each one of these white spheres is a water molecule. Water molecules are attracted to other water molecules. There's bonds between them. So let's look at this center one. It's being pulled down through its attraction to the lower one. It's also being pulled up through its attraction to the upper one. Similar thing left and right, diagonal. So the molecules are being pulled in all directions, but it generally cancels out. The surface molecules, however, they're being pulled down, but there's nothing pulling up. So there tends to be a stronger downward pull, which results in a contraction of the surface. That contraction gives the surface a thin film-like property. So you can see it on display here. So as long as the pressure on the surface is light enough, the water surface can stretch and act like it has a film on it until you break that surface tension, sort of that downward attraction. Once that's broken, then an object's going to fall into the water. So we see that with several different insects. They're light enough to where they can spread out their weight and they don't break the surface tension. So they can they're not floating in the traditional sense. They're actually using the upward force or that extra support from the surface tension. What's really cool is visually, that surface tension causes the water to kind of want to stretch. Like I said, it acts as a film. So we can see that in effect with some of these cool pictures. There's a tiger coming out of the water. See how it acts like a thin film that blankets the face until that surface tension breaks. It also explains why water forms in spherical shapes, why water droplets are spherical. The surface is always trying to contract, and so it ends up wanting to contract into a shape that has the smallest surface area. The shape that has the smallest surface area is actually a sphere. So water, if it's allowed to, will always take a spherical shape just because that decreases the surface area, which is really just a result of the surface contracting. It always wants to shrink itself. And that's surface tension in a nutshell. I'm going to end here. This was my overview of Chapter 13 on liquids.